So guys, is visible? Screen is visible for you?
Yes, sir.
Okay. Yeah, today I'm going to start a new model that is chapter on pure substance. Okay. So in this module, we are having two chapters. One is availability chapter and pure substance. Okay, pure substance. First, I'll do this one. Then after that, I'll do another chapter. Okay. So pure substance. First, already studied homogeneous system and heterogeneous system in module one. Can you tell anybody what do you mean by homogeneous phase and heterogeneous phase? Already studied. Okay, in basic definitions of thermodynamics. Anyone can you share what do you mean by homogeneous system? Anybody can you give example of homogeneous phase, homogeneous and heterogeneous system? Anyone?
So the atmosphere is heterogeneous because of dust particles as well as gas
Hmm.
present in it. And if you
Hmm.
take a pure substance like a
Hmm.
gold bar
Uh-huh.
or a
Uh,
pure liquid nitrogen, all those are
okay.
homogeneous.
Okay. No, in terms of characteristic, how we are going to differentiate? Whatever good examples are there. Then how we are going to differentiate? In what way are going to differentiate? What is the exact meaning of homogeneous system, and what is the meaning of heterogeneous system?
So the homogeneous system will have similar behavior all over the
Hmm. Okay.
volume. The
Okay.
entire volume will have the same behavior.
Hmm.
But heterogeneous, entire volume will have different behavior, like at different points.
Hmm. So
Like
screen. Tell me.
like clouds in the atmosphere are present at certain places, but not everywhere. So when you go and measure certain things at the points where clouds are present, like density of certain substances, it will be different from other places. And if you measure temperatures also over the atmosphere, over the entire Earth, it is different. And but if you take a gold bar, a
Hmm.
very pure gold bar, and you place it at room temperature in a controlled
Hmm.
environment, and you measure various characteristics and properties of the gold bar, over the entire volume, it is expected to have the same properties. So that is
Good.
homogeneous.
Correct. So homogeneous, okay, first I'll tell homogeneous substance means that has the uniform thermodynamic properties throughout the system. Okay, for example, you take water or oil, okay, this is a homogeneous system. On the other hand, it is a mixture of two phases. So if you take water and oil, that is not homogeneous because the oil never mix with the water. Okay, and they are the different phase. Even though they are in liquid state, but they won't mix with each other. Okay, because oil having the less density, it floats on the surface of the water. So it is a heterogeneous system. Okay, one is homogeneous and one is a heterogeneous system. Okay, and so based upon this homogeneous and heterogeneous system, we are going to define the pure substance. Okay, a pure substance is homogeneous in nature and invariable chemical composition. Means chemical composition is same throughout the system and may exist in more than one phase. Okay, so remember that it is a homogeneous and it is invariable in chemical composition. Means chemical composition remains same throughout the system and it may exist in more than one phase. Okay, for example, water. Okay, solid, liquid, and vapor phase. Solid means ice. Next, liquid phase is water and a vapor phase. Okay, mixture of liquid water and water vapor is also homogeneous system. That is an example of pure substance. Carbon dioxide, nitrogen. Okay, mixture of the gases such as the air. Okay, uh, these are the examples of pure substance. Okay, so whenever they ask pure substance, you have to define like that. It is homogeneous in composition, homogeneous in chemical aggregation, means the chemical composition remains same throughout the system, and invariable in chemical aggregation, means the state of chemical combination of the system does not change with respect to time. Okay, these are the three main points related to the pure substance. Okay. Now, here mainly we are going to deal with steam in this chapter. Okay, what is the steam? The different conditions of a steam, how the formation of the steam takes place, and already you studied the steam tables in elements of mechanical engineering. Okay. Can anyone tell me what is the significance of steam tables? Where you are using the steam tables? Steam table. Hope you have done problems on steam table also. What is the importance of steam table? Where you are using the steam table? Okay, steam table. Okay, I'll explain in the further classes. Okay, steam table. It gives the details of steam at various pressure, at various temperature. What is the enthalpy? What is the entropy? Like that, we get all the information using the steam tables. Okay, by knowing the steam table, we can easily find out the remaining properties. Okay, before that, first we should know what is the steam. Okay, already you know steam. It is the vapor of water and it is invisible when pure and dry. So it's difficult to see the pure form of the steam. It is invisible when it is pure and dry. Okay, and mainly in case of steam engines and steam turbines, superheated steam is applied. So whenever you are using normal steam, you will not get the good efficiency because it contains the water particles in suspension. Suppose you are having the water particles, it is very difficult to get the, or it is very difficult to achieve the good efficiency. Hence, in all the steam engines and steam turbines, superheated steam is utilized. Okay. Next, in this class, I'm going to explain how the formation of steam takes place at constant pressure from water. Okay, so that sometimes they may ask, explain the formation of steam at constant pressure from 1 kg of water. Okay, so before that, we are having this diagram and one more diagram is there. Okay, I think you might have studied in elements of mechanical engineering. This is called as HS diagram. Okay, so formation of steam at constant pressure. There are three lines. Okay, so 1 to 2, 2 to 3, and 3 to 4. Okay, I'll explain how the formation of the steam takes place at constant pressure. Okay, so you see there are five diagrams are there. Okay, so you have to show here in the first diagram. We are going to consider uh, the cylinder having 1 kg of the water as working substance and weight is placed on the top of the pistons. So whatever the force exerted by the water and which is balanced by the weight placed on the piston, okay, in equilibrium condition. So we have to balance the condition. That's why weight is placed on the top of the piston. Okay, a cylinder bounded by a piston and a weight is placed over the piston. Okay, starting we are going to consider the 1 kg of water at 0 degrees Celsius and the volume, initial volume of the water is represented as V1. Okay, this is the starting phase. Okay, just it is a basic diagram. Consider 1 kg of water at 0 degrees Celsius and 1 atmospheric pressure. Okay, remember the 1 atmospheric pressure equals to 1.013 bar or 101.325 kilopascal. This is the standard value of atmospheric pressure 1.01325 bar or 101.325 kilopascal. Starting, we considering 1 kg of water at 0 degrees Celsius and 1 atmospheric pressure. Okay, and we are going to supply the heat to water. Okay, at the bottom. Okay, whenever we are going to supply the heat to the water, then the temperature of the water rises. Okay, and meantime, so there will be a change in phase takes place. Okay, so as you supply the heat to the water, So there will be a conversion of the liquid state into vapor phase. Okay, it will not convert at a time. So it will take certain time to convert water into steam. Okay. So when you supply the heat to the water, so that slowly the temperature of the water starts rising, so that 0 to 100 degrees Celsius. When the temperature of the water reaches 100 degrees Celsius, then we are calling it as saturation temperature, and it is represented by symbol Ts. Second diagram. And third diagram, okay, as you supply the heat, okay, then the volume increases, okay, and the water is slowly converted into the steam formation, okay. You see the diagram, this one, okay, this diagram. Starting point one, so we are having the water at 0 degrees Celsius and 1 atmospheric pressure. When you supply the heat, okay, so that the temperature rises and it reaches the saturation point. The point 2 is called as saturation temperature. Okay, so as we are going to supply the heat, it reaches a saturation temperature. So where we are having the two phases of water. That is, one is water, a liquid phase, and another one is vapor phase. Whenever the temperature reaches 100 degrees Celsius, we are calling it as the saturation temperature. On further supply of heat, you remember, on further supply of the heat to the bottom of the cylinder, okay. So that still here we are having the mixture of the wet steam and water phase, okay. For in order to convert completely the water into dry saturated steam, we have to supply the heat. So on further supply of the heat, that uh, on further supply of the heat, okay, all the water particle converted into the uh, steam. Here we are having the mixture of the water and steam. On further supply of the heat, there is no increase in the temperature. You remember, the temperature remains constant. Okay, and at point 4, okay, all the water particles converted into the steam. Okay, so this is called as the dry saturated steam. Okay, so whatever starting we're having, it is the water at 0 degrees Celsius and 1 atmospheric pressure. On supply of the heat, it reaches the saturation temperature. Saturation temperature is the temperature at which the water is converted into the steam. Okay, remember, that is called as saturation temperature. On further supply of the heat, so there is no rise in the temperature, you remember, but all the water particles in the cylinder converted into the steam. Whatever the condition of the steam at point 4 is called as dry saturated steam or simply dry steam. Okay. So this is the diagram 4. First diagram is we are going to supply the heat water which is initially at 0 degrees Celsius and 1 atmospheric pressure. So on further supply of the heat, the temperature of the water reaches saturation temperature. You have to show the diagram 2, and in diagram 3, on further supply of the heat, the water is converted into the wet steam. Okay, and then from between 2 to 3, so that when for further supply of the heat, the water is converted into the steam without change in the temperature. And whatever the position at point 4 is called as the dry saturated steam. Okay. Next, in fifth diagram, you see, okay, as you supply the heat, obviously there will be increase in the volume. You see the diagram. Starting, we are having the initial volume like this. As you supply the heat to the water, so that there will be a volume increases. Okay, so this is the volume of dry saturated steam. Okay, and next, after further supplying the heat, you see this diagram. Okay, so 1 to 2 is the heating of the water from 0 degrees Celsius to 100 degrees Celsius, and between 2 to 4 is it is the heating of water at 100 degrees Celsius and 1 atmospheric pressure. Remember, everything happens at constant pressure only. Means at 1 atmospheric pressure. 1 to 2 is it is the heating from initial temperature. Already we studied ice point and steam point in first chapter. Okay, same concept we are using here. Ice point is 0 degrees Celsius. Okay, so for further heating, it reaches saturation temperature, and upon further heating, without increasing the temperature, all the water particles converted into the steam for further heating. Okay, so whatever saturated steam is there, okay, so it gets superheated. Okay, so for application of steam turbine and steam engines, so they are using superheated steam instead of dry saturated. Suppose you use dry saturated steam, so we will not get the efficiency. In order to achieve the higher efficiency, superheated steam is preferred. So when you will get the superheated steam, on further heating of dry saturated steam beyond the saturation temperature. Suppose we heat the dry saturated steam above 100 degrees Celsius. The condition of the steam is called as superheated steam. Okay. Hence, there are three conditions of the steam. One is wet steam. So it is a mixture of the water particles and steam phase. Okay. Second one is dry saturated steam, means the steam achieved at 100 degrees Celsius only. Remember, all the water particles converted into the steam. Okay, it is dry saturated. And then third condition of the steam is called as uh, superheated steam. So when you get the superheated steam, when you heat the steam above saturation temperature, that is above 100 degrees Celsius, that is called as the superheated steam. So these five diagrams and this diagram is most important. Okay, so in y coordinate you have to take uh, the temperature, and this is called as enthalpy. Okay, H, enthalpy, already studied enthalpy. Enthalpy is also property of the system, and it is given by the formula H equals to U plus PV. Okay, U is internal energy, P is pressure, and V is volume. Okay, this diagram is most important diagram. So here you have to show the temperature. Okay, it is 0 degrees Celsius and it is 100 degrees Celsius, that is called as saturation temperature, and this one is above 100 degrees Celsius, means it may be 100, 200, 300, 400, 500, like that. Okay, so but these two temperature are the most important. Starting temperature you have to take it as 0 degrees Celsius, and then here this one is 0 degrees Celsius. Next it is 100 degrees Celsius, and then it is also 100 degrees Celsius, and heating the dry saturated steam above 100 degrees Celsius will achieve the superheated steam. So this is most important diagram called as TH diagram, temperature enthalpy diagram. Okay. Understood this one, formation of the steam at a constant pressure. Any doubts in this one? Okay, you have to explain with these five figures and this temperature enthalpy diagram. We call as temperature enthalpy diagram. Okay, so I'll repeat once again. It is a formation of steam at constant temperature. So the explanation: consider 1 kg of water at 0 degrees Celsius in a cylinder bounded by a piston. So a weight is placed over the piston. So whatever the weight placed on the piston balances the upward force exerted by the water. According to the Pascal's law, the fluid exerts pressure equally in all directions. We are going to learn Pascal's law in fluid mechanics in fourth semester. So we'll come to know everything. So according to that law, the fluid exert pressure equally in all direction. Whatever the upward force exerted by the water balances the downward force exerted by the weight placed on the piston. Okay. Then, so V1 is the initial volume of the water. Anyhow, pressure remains same. That is 1 atmosphere pressure, 1.01325 bar. So we are going to supply the heat externally to the cylinder. Okay. On supply of the heat to the water, the temperature of the water increases, and then the water slowly starts changing its phase from water to vapor. This is second diagram. Starting here to show it as T1, and second diagram we have to show it as RTS. Okay. On further supply of the heat, the water is converted into the steam. The volume of the working substance gradually increases. Okay. So whatever mixture of uh, water and wet steam, it is in between point, you see, 2 and 4. 1 to 4, and whatever the portion in between these 2 points is called as the wet steam. Okay, wet steam means it is a mixture of water and vapor phase, and condition of the steam at point 4 is called as dry saturated steam. Dry saturated steam, the volume of the dry saturated steam is more. Okay, so that on further supply, once the water reaches the saturation temperature, okay, so there is no change in the temperature, but all the water particles in the cylinder converted into the steam. Okay, so we get the dry saturated steam on further supply of the heat, so that the dry saturated steam is converted into superheated steam. And you remember, superheated steam always achieved when it is the dry steam above the saturation temperature. Suppose you at saturation temperature, you will not get superheated steam. We have to supply the heat. Means when the temperature of the steam is above 100 degrees Celsius, then only we'll achieve the superheated steam. This is how the formation of the steam takes place at constant pressure. Okay, so you have to draw these 5 diagrams plus this enthalpy TH diagram. Okay. So based upon that one, we are going to define these terms. Okay, these 3 terms. Okay, there are 3 phases of a steam. One is wet steam, second one is dry steam, and third one is superheated steam. The mixture of water plus steam. Okay, so in the exam they may ask define the term wet steam. Mixture of water plus steam, that is liquid plus vapor, at the boiling point temperature of water at a given pressure. And boiling point of water is 100 degrees Celsius. Remember, mixture of water and steam at boiling point temperature of water at a given pressure. So next, a dry steam. Okay, dry steam is steam at a given pressure that contains no water particles in suspension. It is also called as saturated steam or dry saturated steam or dry steam. So, here it does not contains any water particles in suspension. Okay, and then superheated steam, when you heat the dry steam above the saturation temperature, that is above 100 degrees Celsius, whatever condition of the steam we are getting, that is called as superheated steam. These are the 3 basic types of steam. Okay, and one more thing here, they will ask draw the TH diagram, TV diagram. Okay, don't make confusion between TH and TV diagram. Whatever I explained, this is a, there are different diagrams. Don't make confusion. Okay, so starting what I explained, it was TH diagram. Okay, temperature enthalpy diagram. So in the x coordinate you have to take enthalpy, and in the y coordinate you have to take T, and whatever the diagram I am explaining, it is of TV diagram. Okay, in the exam particularly they ask sketch the TV diagram for pure substance, pH diagram for pure substance, like that. Okay, so be careful in coordinates. Okay, so whatever I am explaining, this is the TV diagram, temperature and volume diagram. So first you have to draw this curve. Okay, this curve. First curve is a saturated liquid curve. Okay, and whatever line we are drawing, it is called as liquid saturation line. Then we are having the saturated vapor phase, and whatever the line, it represents saturation line, vapor saturation line. Okay, and here wet vapor. Wet vapor means it is a mixture of water particles and vapor phase. And whatever you see, this is called as CP or critical point. In pure substance, we are having the two important terms. One is called as critical point, and second one is called as triple point. Okay. So, anyone can you explain what you mean by triple point? I explained already in the first chapter. Anybody? What is the meaning of triple point? Triple point of water. Anyone? Anybody? Triple point of water.
Sir, it is
Tell
uh,
me.
so for water it is 0.01 degrees Celsius
Correct.
at triple point.
Correct. No, how will define triple point of water? In the definition of triple.
Sir, it is a state actually where solid, liquid, and vapor phase of water together it will be in equilibrium.
Correct. Okay. All the three phases, okay, like solid, liquid, and vapor phases of a pure substance exist in equilibrium condition. That is called as the triple point. And here in this chapter, you are going to study one more point called as critical point. Okay. So the critical point is the point where all the liquid phase is directly converted into vapor phase without supplying the heat. So that is the definition of the critical point. Okay. And there is no distinct phase between gaseous phase and vapor phase. Okay. There is a direct conversion of the liquid is converted into vapor phase beyond the critical point. So you see, the topmost point is called as the critical point. Okay, so that without supplying the heat, so beyond the critical point, all the phase converted into directly the gaseous phase beyond the critical point. That is called as critical point. That's why don't make confusion between the critical point and triple point. So triple point is the one in which all the three phases of a substance exist in equilibrium condition. Critical point is the one in which the phase of a pure substance is directly converted into the gaseous phase without supplying the heat. Okay, that is called as the critical point. And you see, don't make confusion between here saturation liquid line and saturated vapor line. These are called as the superheated vapor line. Okay, so whatever line, the first line is saturated liquid line, second line is saturated vapor line, and third one is called as critical isotherm. But all the points, all the lines you have to draw through the critical point. This starting from this point, ending at critical point, and then from critical point onwards, you have to draw the vapor saturation line and superheated SEM. There is a more deviation of superheated vapor line compared to the vapor saturation line, and these are called as critical isotherms. Okay, we are having all these concepts in real gases. I'll explain all these concepts in module 5. We are having a separate chapter called as ideal gas and real gas. So in the ideal gas, where real gas, we are having equation called as van der Waals equation. Okay, there I'll explain this diagram. Okay, so we are going to draw this diagram, then we are going to derive that van der Waals equation in real gas. Okay, before that, just you should understand the nature of pure substance in terms of temperature and volume. Okay, See, beyond up to critical point, the temperature increases. After that, we say, you see, like this, we are having the nature of curve, temperature versus volume. Okay. And certain terms you should remember. Okay. The first one is heat of vaporization. Once again, in this chapter, we are having lot of definition like define pure substance, define a triple point, define critical point, like that. We are having lot of definition. First, you have to understand the definition. Once you understand the definition, it is very easy to solve the numerical problems. Okay, and you are going to learn steam tables. How, what are the properties of steam table? How to take the steam properties and how to find out the remaining properties of the steam in this chapter. Okay, I'll explain in the next class how to see the steam table and other things. Before that, in this class, we are going to learn the basic concepts of pure substance. First term is heat of vaporization. Okay, so how we are going to define the amount of heat required to convert the liquid water completely into vapor. Okay, see in the diagram, this one, this diagram. Okay, so this is called as heat of vaporization. The amount of heat required to convert the water at saturation temperature, that is called as heat of vaporization. Okay. Can you tell me other name is there for this one? What is the other name? There are two terms. One is the latent heat and one is the sensible heat. Okay, anybody? What is the difference between latent heat and sensible heat? Okay.
So latent heat is heat
Hmm.
that is present in the substance when change of phase is occurring, and it cannot be measured using a
Hmm.
thermometer, but sensible
Hmm.
heat can be measured seeing the
Correct.
rise in the thermometer liquid.
Correct. Correct. Okay. Correct. So first one is sensible heat. Okay. So as I said, during the supply, the heat temperature of the water changes. Okay. So whatever the temperature between 1 and 2, okay, that is called as sensible heat. Amount of the heat required to convert 1 kg of water at 0 degrees Celsius to the 1 kg of vapor phase at saturation temperature. Okay. So this includes both water and water and the vapor phase. Okay, it's a conversion of 1 kg of water, amount of the heat required to convert 1 kg of water at 0 degrees Celsius and 1 atmospheric pressure to saturation temperature, up to saturation temperature. So that is called as sensible heat. Okay, then whatever portion is there in between this line, straight line, that is called as latent heat. Okay, latent heat means the amount of heat required to convert 1 kg of water at saturation temperature. Okay, so here starting you are going to take 0 degrees Celsius. While defining the latent heat, so you have to change the definition. The amount of heat required to convert 1 kg of water at 100 degrees Celsius at saturation temperature to 1 kg of dry saturation steam at the same temperature and given pressure. That is the definition of latent heat. Amount of the heat required to convert 1 kg of water and saturation temperature to 1 kg of dry saturation steam at saturation temperature and at the same pressure. That is at the given pressure. That is the definition of heat of vaporization. Or it is also called as the latent heat. Remember, latent heat or heat of vaporization both are same. Okay. Next, saturation temperature and saturation temperature. The temperature at which the vaporization takes place, that is called as a saturation phase. Okay, the temperature at which the vaporization takes place, that is called as saturation temperature. Okay, saturation temperature means in case of water, the water starts boiling at 100 degrees Celsius. And then we are having two more terms called as subcooled liquid and compressed liquid. Okay, you see in the diagram, not that. So definition of subcooled liquid is subcooled and compressed liquid. If the temperature of liquid water on cooling becomes lower than the saturation temperature and at the given pressure, that is called as subcooled liquid. Temperature of the liquid water on cooling, you remember, on cooling becomes lower than the saturation temperature. Temperature of the liquid phase on cooling becomes lower than the saturation temperature and at a given pressure, such condition is called as subcooled liquid. Okay. On the other hand, we are having the compressed liquid. Compressed liquid means when the pressure of the liquid is greater than the saturation pressure, okay, at a given temperature. So we are having saturation pressure, saturation temperature. So condition of the steam at saturation temperature and saturation pressure. When the pressure of the liquid is greater than the saturation pressure and at a given temperature, that is called as the compressed liquid. Apart from this one, we are having the superheated temperature. Okay, superheated temperature means, as I said, so you are going to achieve superheated steam when you are going to supply the heat above the saturation temperature. When all the liquid has been evaporated completely, means there is no water particles in suspension and heat is further added, then the temperature of the vapor increases. Okay, when the temperature increases above the saturation temperature, then the vapor phase is called as superheated vapor. Superheated vapor is achieved by heating the dry saturated steam above the saturation temperature. That is called as superheated temperature. Okay, so one is saturation temperature and one is superheated temperature. Okay. Next, degree of superheat. Okay, so we are having one more definition called as. Hope you understood the saturation temperature and superheated temperature. So that is the temperature when the temperature increases above the saturation temperature. That is called as superheated temperature. Saturation temperature is boiling point of water. That's nothing but 100 degrees Celsius. And third term is degree of superheat, the difference between superheated temperature and saturation temperature at a given pressure. For example, so 300 degrees Celsius is your superheated temperature and 100 degrees Celsius is the saturation temperature. Then degree of superheat is 300 minus 100, that is 200 degrees Celsius. So it is a difference between superheated temperature and saturation temperature and at the given pressure. So, and one more important term, okay, when the pressure is greater than the critical pressure, then the liquid water is directly converted into superheated steam. Okay, so whatever the pressure is greater than the critical pressure, you see the diagram. So here, whenever the working substance having the pressure greater than the critical pressure, all the liquid is directly converted into superheated steam. So this is one of the important point. Okay, so we studied temperature enthalpy diagram. Okay, second one temperature volume diagram. Okay, we studied first one pH diagram, that is formation of the steam at given pressure, the pH diagram. Second one we studied the temperature volume diagram, and third one we are going to study. So this one is called as a PP diagram. Okay, pressure versus temperature diagram. Pressure you have to take in y coordinate and temperature in x coordinate. So you remember the nature of curve, how you are going to draw in a TH diagram and in uh, PV diagram, and then we are having a PP diagram. This is the PP diagram. So be careful about X and Y coordinate. In the Y coordinate, you have to take pressure, and in the X coordinate, you have to take the temperature. So first you have to draw this line. This is called as sublimation curve. Okay, and this is a triple point. Okay, so next you have to draw two lines. One is the fusion curve, and one is called as the vaporization curve. Okay. Vaporization curve, and I say the pure substance exists in three phases. Okay, one is solid phase. Okay, you see the solid phase is the phase between fusion core and sublimation core. Whatever the reason we are having in between fusion core and sublimation core, that is called as solid phase. Okay, and then you see, so this is called as your liquid phase. The portion between fusion core and vaporization core is called as liquid phase, and then so this one is your vapor phase, and this is your triple point. You see the triple point is the point where all the three phases, solid, liquid, and vapor phases of a substance, a pure substance, exist in equilibrium condition. That's why you have to show triple point here, and here it is at the top. You have to show critical point. That's why you don't make confusion between a triple point and a critical point. So you have to show triple point here only and critical point. What diagram I'm explaining, the most important diagrams, you have to practice all these diagrams. One is TH diagram, second one is PV diagram, first one is TH, TV, and then PT. These are the three diagrams. Okay. This is a sublimation curve and the vaporization curve, and then we are having the fusion curve. Okay. So sublimation, vaporization, and then fusion. So you, when you'll get this one, how the liquid is converted into vapor phase when you supply the heat to the water. Just now we studied. Okay, so you have to concentrate on this one: solid phase, liquid, and vapor phase. Vaporization. Okay, there are three terms. One is vaporization, one is sublimation, and one is condensation. Vaporization means uh, the amount of heat required to convert 1 kg of water to 1 kg of steam. That is called as vaporization. There is a change of phase from liquid to vapor. Second one is condensation. Anybody, what do you mean by condensation? So there are two terms. One is boiling and second one is condensation. These are the two things you are going to learn in heat and mass transfer in sixth semester. What is condensation? Condensation, anybody? Okay, I'll explain. One is evaporation and one is a condensation. Evaporation means there is a change in phase from liquid to vapor. That is conversion of steam uh, from water into steam. That is the example of vaporization. Condensation means it is the conversion of vapor phase into liquid phase. That is called as the condensation. And one more is there. That is conversion of solid phase into vapor phase directly. That is called as sublimation. Okay. Anybody give the example of sublimation? Means conversion of solid into vapor phase directly. That is called as sublimation. Very good example of sublimation is camphor. Okay, where solid is directly converted into vapor. Like that, do you have? Do you know the conversion of vapor into solid? Any example? Solid to vapor, good. Any example related to vapor to solid directly?
Sir,
Ammonium
ammonium
chloride.
chloride.
Okay, converted from vapor to solid. Good. Okay.
Yeah.
Can you give an example of condensation? Conversion of vapor into liquid.
So when it
Ah,
rains, that is condensation. Water vapor, the water evaporates, it becomes vapor due to the low temperature in the cloud. So condense to liquid.
good. Good example. Okay. So, like that, you have to analyze the practical example of the three phases. Okay. First, you should know what is pure substance. So, what are its properties? How the conversion of the one phase is expressed into another phase. Okay. How much amount of heat is required to convert that one particular phase into another phase. Okay. These are the things we are going to learn in pure substance. Okay. So these are the three things you remember: vaporization, conversion of liquid phase into the vapor phase. Next, second one is condensation, conversion of the vapor phase into liquid phase. And third one is sublimation, conversion of solid phase into vapor phase. And camphor is the best example of sublimation. Okay. Next, what I said. So sometimes they used to ask, define the term sensible heat. Okay. As I said, it is the amount of heat absorbed by 1 kg of water when it is heated from 0 degrees Celsius to boiling point. Okay. Sensible heat is the amount of the heat supplied to 1 kg of water when it is heated from 0 degrees Celsius to boiling point. It's nothing but your saturation point. Okay. This is the definition of sensible heat. Okay. Whatever I have shown in the diagram, pH diagram, it is there. Okay, pH diagram. So whatever T temperature, the amount of heat required to convert 1 kg of water at 0 degrees Celsius to 1 kg of water at saturation temperature, that is called as sensible heat. That is the definition of sensible heat. Okay. The second definition is your latent heat. What I said, heat of vaporization or latent heat. So, and it is represented by, here you have to remember a symbol also. HF is the notation for sensible heat. Okay, same thing you are getting in the steam table. So, whenever you are having HF, so you recognize it as sensible heat. And latent heat, or it is the heat of vaporization. That is latent heat and represented by symbol HFG. Okay, HFG, it is the amount of heat required to convert 1 kg of water at saturation temperature to 1 kg of dry saturated steam at the same temperature, means at saturation temperature and at the given pressure. That is the definition of latent heat. Okay, and HFG is used to represent latent heat. So just by seeing the diagram only, you have to define sensible heat, 1 kg of water at 0 degrees Celsius at given pressure to 1 kg of water at saturation temperature and at the given pressure. Second one is latent heat, a conversion of 1 kg of water at saturation temperature at the given pressure to 1 kg of dry saturated steam at the same temperature, that is saturation temperature, and at the given pressure. That is the definition of latent heat. Okay. Then one more is there. Okay, total heat or enthalpy of wet steam. Okay. So how we are going to define the enthalpy of wet steam is, it is a summation of sensible heat and latent heat. So in terms of definition, it is defined as the amount of heat required to convert 1 kg of water at 0 degrees Celsius to 1 kg of wet steam at constant pressure. So HF plus HFG. Okay. So you see HF is this portion and HFG is this portion, whatever the portion between 2, 3 and 4, and total enthalpy means between 1 and this point means the summation of sensible heat and latent heat. Then how we are going to define? So it is the amount of heat required to convert 1 kg of water at 0 degrees Celsius to 1 kg of dry saturated steam at the saturation temperature. That is the definition of the total enthalpy. Suppose if they ask only latent heat, you have to take only the straight line. Okay. And suppose they ask sensibility, you have to take this one, and total enthalpy or total heat is the summation of sensible heat and latent heat. And in definition, we are going to define as the amount of heat required to convert 1 kg of water at 0 degrees Celsius to 1 kg of dry steam at saturation. Okay, that is the definition of total heat. Okay, then already we know superheated steam. When we are going to heat the steam above saturation temperature, that is called as superheated steam. And one more is there, that is called as degree of superheat. Degree of superheat is the difference between superheated temperature and saturation temperature. And one more is that total heat of superheated steam formula you should remember H sup. H sup means superheated steam. HF, it is a summation of sensible heat plus your latent heat plus the heat required to convert 1 kg of dry steam into 1 kg of superheated steam. So whenever they ask, find out the enthalpy of superheated steam, you have to remember this formula. H superheated equals to HF, sensible heat plus latent heat plus CPS into T sup minus TS. CPS is nothing but it is a specific heat of superheated steam. You remember we studied a specific heat at constant pressure and specific heat at constant volume in module 2. Like that, we are going to study specific heat of superheated steam, and it is always 1.3. You remember, suppose the value is not given in the problem, so it is 1.3. Okay, so value of superheated steam. So HF enthalpy, HFG is this is a sensible heat, and this is the latent heat, and this is the total heat. I hope you understood. Concentrate mainly on the definition. What is the pure substance? How the formation of steam takes place at constant pressure. Okay, that is most important. You have to explain with 5 diagrams and 1 TH diagram. Okay, we studied next PT diagram. You have to show triple point and critical point, and you have to show 3 curves: vaporization curve, sublimation curve, and fusion curve. And then we studied one more diagram. It is a TV diagram. So these are things we studied. Meantime, we studied the definitions. So all you have to go through the definition properly. Whenever they ask definition, so you have to write in that in terms of technical meaning. Okay, so amount of heat required, like that. You have to put the technical term. So we'll discuss some more concepts on pure substance in the next class. So those who have not entered your USN, please enter in the chat box. Okay. Please enter in the chat box. Once I stop the recording, it is we cannot recognize the attendance. That's why you all of you have to enter now only the attendance, your USN in the chat box. Okay. Thank you one and all. I'll stop the meeting now.